Hello, everyone. Good afternoon, good evening there, and thanks for joining our talk. This is really the first time, me and Ebrahim, presenting in this summit, and very excited to, share some of the, our impractical experience, and also certainly talk with more people here. So first, a quick introduction of the company. Actually, you can see it's called a Mist, a Juniper company. Mist was almost a 5 to 6 year old startup. It was founded in 2015 to really solve this network operational problem, use big data and machine learning. And Mist got acquired after 4 years. Startup journey got acquired about 1 year ago by Juniper networks. So now we are part of the big Juniper family. And our talk today is automated pipeline for large-scale neural network training and inference, in which we are going to talk about the theory and also the MLOps of a real model example in the solution we built. Just a quick introduction of myself. My name is Jisheng Wang. And I have been mostly working in the enterprise industry in the last 12 years, applying big data and machine learning to solve different enterprise problems. Before me, I was mostly focusing on enterprise security, and now it's enterprise networking. So I will let Ebrahim talk about himself.
Sure, absolutely. Thank you. First of all, hello, everyone. I hope everyone is staying safe and healthy during this pandemic time. So I'm happy to have this presentation. About my background, I have a PhD in electrical engineering about cognitive learning networks. And after my PhD, I have worked in different areas in data science, including information retrieval. And now I'm working with MIST. Around 3 years I am with MIST. So I have worked in different projects, including inference engine for the chatbot that we have, and anomaly detection, outlier detection, and now we are working through different projects. So I'm here to share some ideas that we got through the development of anomaly detection and scaling that into production.
Yeah, so before we jump to the details about the model, I want to spend some time, because probably most of the audience are new to this industry. So just to probably spend a few minutes talking about really what's the business problem we try to solve here, especially as a startup before. So as you may know, Wi-Fi actually has been in enterprise industry for almost 2 decades. And Wi-Fi started as what we call good to have, as a more convenient way for user to connect, like say guest network. This is the best example. And fast forward 2 decades, 20 years, today Wi-Fi is not only good to have, but a must to have, and become one of the key factors for the business success, even across all different industries. I just want to give you one example of it's really a customer example. We have a very large e-commerce customer, and they run the whole network inside their distribution center with Mist. And they run robots in the distribution center, to help packaging and shipment. So what they told us, if the Wi-Fi connection stops for 5 seconds, the robot will just get stuck there. If one robot stuck, then all of the neighboring robot will also just stop. So this will certainly delay the packaging, shipment, and finally cause potential business loss, because their customer can return the package if it's delayed. So they actually can translate each of this minute or hour of the network incident into really the dollar numbers for their business loss. And the number we heard actually is around 20 million, more than $20 million potential business loss for 1 hour of the network incident. So this is really the business impact and also the opportunity for this area. So as an individual, probably most of the experience with network is about Wi-Fi. When you go to an office, you just connect your phone with your corporate Wi-Fi. But and you know, this just shows like when the network sucks or you have a problem with connecting to the network, you always think it's a Wi-Fi problem, which is not true. 50% they are the Wi-Fi problem, but actually most of the time, or even the other half of the time, it's more beyond the Wi-Fi. So this graph shows this end-to-end diagram of what the enterprise network infrastructure looks like. You can see there are many segments. They're wireless. This is what you experience as individuals. Behind there, there's wide, there's a firewall, you know, SD-WAN, and finally a mix of this data center, private, and public cloud. So unfortunately, this end-to-end network so far today is still designed as most of the places is single point of failure, which means if any of the hop has a problem, it will impact the end user experience. So this is really, and also with the traditional human-driven the network operational procedure, if any of this problem happens, it may take hours or even days, sometimes a couple of days, to really find the root cause of the problem and remediate the problem. So as I mentioned before, all this can cause a business loss. So this is the reason we created this actual feature called Marvis. Our goal, which targets to automatically detect, troubleshoot, and even remediate the problem. You know, this is the kind of the high level, we call it a self-driving network. So, you know, before we do a deep dive of our model, you know, the MLOps, I want to really, you know, look at the high level of this big data solution we create. So most of the enterprise solution is trying to solve this problem called finding the needle in the haystack. So it's really a data funnel. From the input side, you want to take as much variety and volume of the input data to enhance your visibility of the problem space. But on the output, on the bottom, you want to give user as compact and as price actionable insights as possible. So rather than just providing user with overwhelming dashboards or even noisy events, you can see that's one layer in the middle. We added two more layers for the automated troubleshoot and the actions. As I mentioned, one big differentiator of this AI solution we created is to take automated action based on the ML result to remediate the problems. Yeah, this is kind of the diagram of really the components we build inside this self-driving network solution. This is called the event action framework. First, it's all built on top of it's a cloud native solution. It's a SaaS offering for our customer. It's built on top of AWS and now moved to GCP, migrate to GCP. And we use all of this open source big data and machine learning tools and the libraries. And there are really four layers we build here. First is data collection. And one thing I want to point out there is we care about not only the network device, but also the user and application experiences. You know, we collect a lot of data to cover that. The second layer is event generation, in which we use various types of the supervised and unsupervised model to really collect the events and the signals. And anomaly detection is one big part of that. The third piece is the diagnosis. The goal is to use different spatial and temporal correlation models to really find the root cause of the incident. What happened in your network caused this incident? Finally, based on the root cause, you know, we can either take an automated action if we have the control of the device. If not, if it's in the neighboring system, we give you the suggested actions to guide them, you know, step by step to remediate the problem. And finally, as Ebrahim mentioned, we also build a kind of an NLP-based chatbot to help them more like the help desk people. When they, you know, you bring your laptop to them for any of the issues, they can just talk with a bot to get the answer probably in a couple of minutes. So this is a high-level picture of this self-driving solution we built. And next, I'm going to hand over to Ebrahim to talk about that anomaly detection use case here.
Okay, Awesome. Thank you, Jisheng, for the introduction and passing the big picture. So in this section, I would like to pass how we are building anomaly detection, and we leverage that into production environment. So the first thing is that anomaly detection is really used in our use case is trying to detect some temporal or spatial information anomalies which happen throughout our system. Hypothetically, we are looking this very well-defined anomalies. However, this is not really the case. So in our case, anomaly detection helps us a lot for monitoring in the scale that we are monitoring. So it helps us to have the paradigm of proactive monitoring rather than waiting for people, customers to call us and make a complaint. In a lot of cases, we catch a problem without even being a problem before it's getting a problem. So the journey of anomaly detection at MIS has been, we started with some rule-based heuristic models, and like people should be connected for the majority of time, putting some threshold rules there, but soon it failed. And then we moved to more statistical models, moving average, online ARIMAs, and none of them were really able to pass the expectations. Essentially, the false positive is a killer factor for us, and we have to be very cautious on this one. BiLSTM neural network was the first time that we were able to pass something that everyone was happy about, that very precise and also with very low false positive signals. Okay, so anomaly detection in practice is baselining the key performance indicators that we have. So in our use case, we have tens of thousands of sites that we want to monitor. And if you, I pass some examples here. As you can see, we have a wide range of variety of patterns that we have. So you can think about warehouses, as Jisheng was giving examples. We have offices, we have shopping centers, and many different type of patterns we experience. So some of them you have seasonality factors, some of them they don't have anything specific. So that's something. On the other hand, there is no one single metric that people care about. It's a combination of metrics that people care all together, right? So to that purpose, we are designing anomaly detection about a multivariate time series where the input is a vector of time, vector at each time. So then comes that, what feature do people care about? This is a very important question when you want to design anomaly detection. Specifically, if you think about that, everything that we discuss here as a data scientist is in the realm of statistical analysis. Essentially, we are capturing a statistical anomalies. However, people care about user impacting anomalies. So to close the gap, you have to work very closely with user to make sure that you are covering all the cases that they care about. And for my case, I have worked very closely with customers. Sorry. Oh, my nephew is here. I'm sorry. So this is the type of challenges that we have with online presentation. Hold on. Give me. Sorry, I apologize. That's my nephew. Okay. So back to the talk. So in our case, I have to work very closely with customers to make sure that I'm covering parameters that they care about and capturing the key performance indicators. So in the case that we are analyzing, like success and failures seem like trivial things that we want to monitor. We call it SLE, service level experience features. And then we had some spatial features here. You can think about like when failures happen, say that you have one client that is failing 100 times. It's very different from the time that you have 100 failing clients, right? To distinguish, we are adding these spatial features. So like the unique number of clients, unique impacted clients, and so forth. And the other thing that we have is that state of the network. For example, if network is failing on authentication, it's very different from the network that is failing on association. So not all the failure types are the same for network admin. So we added this state feature to that purpose. And the other thing here is that, like you saw in the examples that I passed, is that we have seasonality factors like daily or weekly. And in all type of models that we try, models have short memory about remembering this trend and seasonality factor. To that purpose, we explicitly added some seasonality factor, in this case, like hour of day and day of week, to pass these seasonality factors. Okay, and now comes challenges about the ML part. So one part is that, first of all, what is abnormal? Essentially, anomaly by definition is such a rare event that you don't know ahead of time what you are expecting. So this is some challenge that we have to face. The other thing here is that this is not a very well-defined supervised problem. You don't have a good well-defined labels here, that cat and dogs, that you can go ahead and classify them. So to address these challenges, what we did is that we decoupled the prediction and detection. Essentially, we try to see what we can do about prediction and try to use that prediction to make some detection. So we change the paradigm. Rather than predicting what is abnormal, we try to predict what is normal. And then when you have normal, when you're trying to predict normal, now out of the blue, you have a lot of label data. You can't use the self-supervised or semi-supervised to predict at each timestamp what is happening next timestamp. So now you have implicit labels for your data. The other challenge that we have to address for anomaly detection is about confidence. Anomaly detection is all about confidence. So no matter what model you are training, it's going to make some prediction. But the fact is that the important factor here is that how confident is the model about its prediction? Is it certain or is it uncertain? Is it taking any risk, right? So somehow we have to add the notion of confidence to our models. It does make sense, like think about that. If a model is predicting 0, is it between -1 and 1, or is it between -100 and 100? So you have to have some notion what is the output distribution. When you are using neural network to make to have some confidence in your prediction, it's not very trivial to add that notion to neural networks. So one of use cases, one of just not many of neural networks that have this idea of confidence integrated in them is Bayesian neural networks. And in Bayesian, you're trying to add probability distribution concept to neural networks. So, and it turned out that when we are adding dropout to neural network, somehow we are adding Monte Carlo sampling from our neural networks. So what people do in this case is that they try to, when you train a model, you train it with dropout. And when you go to inference, you take that dropout off of your network and you try to make a prediction. So, but what you can do is that you can keep the dropout even during the inference and then make samples from the output. So rather than just making one inference, make the number of inferences. Now you are taking sample from the output and then you can use it to get the probability distribution of the output of the model, right? To give it in practice in testing, I try to use a sine wave testing. Since data that we have, it has some type of seasonality factor, and sine wave is a very good thing for testing here. So I was using a simple sine wave signal here and was trying to see if the model is capable of handling the output and give us a good prediction interval. As you can see, the gray area is our prediction interval. The blue line is the real value. As you can see, look, the interval, the prediction interval is not really that tight. In fact, it's a very wide margin that we are passing. So it doesn't seem very good model, in fact, for us. To improve that one, we had a novel model here. So we try to train the model with confidence. So I'll explain this one. So the reason that the model was not able to capture the behavior, the probability distribution of output was the inherited complexity of the neural network, the inherited uncertainty of the model by itself. So you have thousands of, hundred thousands of, millions of parameters that you want to figure out. So the model is uncertain about those parameters. And when you are making dropout as sampling from the network, is not just taking sample from the output is taking sample from the whole network, right? So you are taking uncertainty of the model into what you are trying to take sample of, right? So to overcome this challenge, I introduced the idea of training with confidence. So in this case, what I do is that at each timestamp, I have a sliding window that, and then it's trying to find the maximum, the average, and the minimum of the values there. And a lot of time is really about time coherence of the signal that you are monitoring. And then now you are trying to have 3 values for each prediction that you make. So then at each timestamp, we are predicting the augmented output, not really one single value. We are using 3 values for each prediction. And when I put it in the sine wave test, you see that the interval, the prediction interval is very tight, really, and it's following the real signal very closely. And that's the model that we use for our prediction and our detection. Okay, so then just putting that into the some type of predictive model. So we had the vector input, and it goes through the predictive model, and we are trying to predict what would be the output in the next time stamp, right? And in our case, we are using augmented output, essentially the minimum, the average, and the maximum thing. So for this predictive model, I use BiLSTM model, a very simple BiLSTM, in fact, here. So we have around 100 hidden nodes. Each of LSTMs gets 50 hidden nodes. We have a recurrence of 12, essential. It means that we look at last 12 hours. In our case, we aggregated data hourly. I'll explain about why we are going with hourly toward the end of this session. And then we make a prediction for the next timestamp. And then the next layer is a dropout to make the network robust. And then we have a dense layer. Is my I'm sorry. It seems that my nephew wants to play really. Okay, so then we have dense layer to map to the number of outputs that we want, to the dimension that we want. In overall, we have something around 27,000 parameters. Reasonably very small model. Okay, so we changed our detection so far to a prediction problem. So now we are trying to predict what is happening in the next timestamp. Here we have some examples of what has happened for like different sites. So like one site that you can see, the first graph at top at right. So it's a very non-stationary thing. This is one of cases that like the classical models have really difficult time in modeling this behavior. But by adding the seasonality factor and time parameters and the nature of LSTM, we were able to capture what is happening with these sites. And as you can see, the interval and also the prediction has followed the real signal very closely. The second one and the first one are cases that most likely traditional models can capture. However, here also we have very good performance, specifically if you look at this one, like we are following noise very well. Sorry, just give me another second.
Now you can hand off or let him talk about the remaining of your presentation. Maybe like while we're taking some break here, if you have any questions or anything, you can put in the chat room now. I think we have probably another 10 minutes, maybe a little bit delayed, 10 minutes on the ML ops side. Really talking about now is the theory piece, and we're going to talk about the productization. The main challenge here, for this model is really, this is an unsupervised model. We have to train one model per customer per site. Even you think some of the retail customer like Walmart it's not a one model for all of this. For the better sensitivity, we have to train one model each site. And we end up have to train in more than 15,000 neural networks models every round in the cloud. I think Ebrahim is going to cover some details about that.
Sorry, everyone. I apologize for this one, for the inconvenience. So let's go back to the, I see that there are some questions. I think that it's easier if I take questions toward the end of the
Yeah, please go ahead, Ebrahim. Let's finish all of this. I think we're a little bit delayed here already.
Okay, sure. So now the summary of this one is that now that we have moved to prediction, now we can talk about the prediction error. In this case, we have a very good performance. In fact, we have 1 to 5% of normalized error. And this is a very good performance that we are achieving. However, we don't forget that we are talking about anomaly detection. We have to map this one to anomaly detection. The thing that is happening here is that now we have trained models, hundreds of models, and we are evaluating performance of sites every hour, right? So it means that we have a lot of independent prediction across sites, right? When you have that many independent predictions, so you will end up with a Gaussian, a multivariate Gaussian distribution. And when you have this, for error, I mean, so when you have this multivariate Gaussian distribution, then it's easy really to go and think about 3 or 5 sigma rules. Now, what is happening is that, so you have this probability distribution for error, a Gaussian probability distribution for error, and then you can now see who is deviating from the 3 or 5 sigma rules for the multivariate distribution. And that's how we are mapping our prediction to detection, right? And on the right-hand side, you can see like how signal is really distributed. Pretty much more or less is a very sharp spike at the middle, and then you have the it's decaying very fast. So now talking of this one, that's what we have done for the model, and now we want to go ahead and deploy that into production and scale that across all the systems that we have. From the pipeline perspective, the technology stack, we are a shop for open source systems. So we are using Kafka to pass messages and events and process, get that to where we want to process them. We have the secure backup system where we are trying to back up our data, our Kafka into S3 in our case, or storage in, through GCP. And then we have Spark job on EMR trying to read and process data from S3. We have Airflow for scheduling all the things that we do. And then when we process result, we persist that whether in Elasticsearch or write that back to Kafka or persist that in S3 again. So the model life cycle here, so more or less this is a generic life cycle. We have the training, we have verification, serving, and feedback. So for the training process, we have long-term retrieval of data that we have. For our case, for example, we can go far as like 2 months or more. And then for verification, however, is not very trivial. How should we process this one? If you think about this one, we had unsupervised system. And when we have unsupervised model, we don't have really label to go and verify the model against those labels. To do so, we try to use the notion of global intelligence that we have and try to use that knowledge. I'll explain each section in details in following slides. And then we have the serving model. For serving, this is a short time retrieval that we are retrieving, something around 12 hours that we were designed the model for. And then we have the feedback. This is where human is in the loop. And when we have human interaction mostly happening through the whole ecosystem. The model training. So here in the right hand, you can see that first we have data is read from S3 buckets, and it goes to EMR cluster, and then on each executor, then data goes to each executor based on the site ID that we have. And each executor loads TensorFlow and train a model for one specific site. So in this case, we have many small models, right? So we are training distributed, but we have small models trained on each executor. And then when the model is trained, we persist data into S3 bucket, the binary format of the model into S3. So that job, since we can go very far, like 2 months worth of data for that job, it could be a weekly training or it could be triggered on demand. So like I show you one case that we have triggered on demand and why we have done that. The other thing to pay attention here is that the way that we are distributing is that we are distributing training, but we are training single model on each executor. The alternative of this one is that if you had one big model and you want to distribute training for one single model, that would be a different paradigm. And in fact, we are using that one for a different problem, the problem of outlier detection, where we are training a very universal model, a big universal model, and we have a lot of data. So we are distributing training for that one single model. Now it comes to model verification. We have trained, and now we want to verify whether this is a good model or not, then we have done a good job in training or not. So as I said, this is unsupervised model. We don't have label really to go verify against of that. But what we have here is that the notion of global and versus local intelligence. We have trained models in many different batches in history, like in past. So for example, last few years, we have a train model every week. Now we have an idea how would be the error for each training batch, right? And now we have a new batch of train. That is the local intelligence that we have. So we want to somehow to verify if the train is normal or not. We can go ahead and try to statistically match the behavior of these two set of like the knowledge that we have. Now we have to map that knowledge to some type of distribution. We are using empirical probability distribution, and we are comparing the local probability distribution, the most recent batch of training, with what we have done in past few months, and we try to see if everything seems normal. And that's how we are really verifying. To do that, we are using KL divergence. Essentially, it shows how far these two probability distributions are from each other. And to that practice, for most of the time, we can do that without any human supervision. And not always, but for most of the time, we don't really have anyone really go and interact with this system. And then it comes the model serving. So that's the serving. For the serving, what we do here is that we are reading the data, the short-term. This is a mini batch, so we are looking at short-term data. We are reading from S3 buckets here, though it goes through the EMR cluster. Each executor fetches the corresponding model for that site and then serve for that specific model that is designed for each site and make some predictions. Some of them, they are normal, and some of them, they are abnormal. Like you can see that here we have at the lower part, we have one anomalous site that we have detected. We have decided to go with hourly data. Essentially, this hourly data was not really a constraint of the system, like the pipeline. It was a constraint of the precision that we want to have. We want to have very high precision, very low false positive thing. So when you are talking about false positive, and the confidence of the signal is that if you have the good signal to noise ratio. So it was some design decision that really we ended up with hourly. In other different models, like outlier detection that I was talking about, we go really very short time window, as low as few minutes. Then the part that is not very trivial, really, how we have to handle it, it needs human interaction, it's not automated completely, is where we are integrating the feedback into our system. A lot of times, I mean by feedback, like negative, when we are failing at detection, or maybe we have false positive. So it requires debugging, and a lot of times it ends up with revising hyperparameters in our case, like whether verification parameters, like the models that we have verified, they have changed. Like one of the cases that we have recently involved changing hyperparameters for verification was that after pandemic, the coefficients of training are different from what we have before pandemic. And then I had to go ahead and try to limit the time window that we go back for the global intelligence. And sometimes it's a model adjustment, like what we are trying to predict as output, or what we are really passing as input. Like the feature selection at the beginning was a conclusion of trying to pass seasonality factor, and then we added explicit seasonality factor. So I want to wrap up my talk with some graph from how we are scaling here. So more or less, we are growing the number of sites. The site growth is having a linear pattern here. So in the top, you can see that the number of sites are increasing almost linearly. And then we have automatic scaling, which can conclude to having a constant time training. And the second graph that you see here, more or less for all the training, no matter how many sites we have less than around 20 minutes of training time for the whole, serving time for the whole, I made a mistake here, not the training, it's the serving time for serving all the sites. And as you can see, this is a constant time. The most important factor for the whole practice of anomaly detection for us, it was the complexity of operational complexity, where user need really, now we get alerts, and now we have to go and analyze anomalies. And what we can see here is that we have a constant time complexity here. Number of anomalies are very constant, like despite the fact that we have a linear increase in the number of sites that we have, the number of anomalies are more or less constant here. We have these spikes here, and this is like cases that like required human intervention here. That was the case that one of the big customers with many sites decided to change some parameters about their site, and so it introduced man-made anomalies to the network, and it increased the serving time and also the number of anomalies that we have seen. And that was my last slide. So thank you for being patient, and I apologize for the inconvenience. So now I would like to open it to questions. So Jisheng, do you want to go through questions? And
we have, I just try to cover most of the questions. There are not many actually in the chat room, and there's a new one coming. Did you have set the metrics for each model?
So the model is like each model, not specifically, we have all these aggregate values. So like for verification of the training job, we are using this global like probability distribution. This is global. And even for verification like training thing, so we are training model per site. So like we are taking into account the loss for each site. However, verifying the whole training batch is a global thing. So it's a combination of both really.
Yeah. So the next question is, how do you handle CI/CD for your pipeline? Actually, that's a very good one. You know, this first, this is how we build the product here. And our data scientist team actually have data engineer, even DevOps people in the team. So we take the end-to-end ownership of the product. Actually, we even directly deal with the customers to really understand the problem. So for CI/CD, we leverage almost all of this cloud-based tools. Like we use, like Ebrahim actually showed, all of the graph are from SignalFX. So we have different metrics from the system level, like say how many nodes we launch, how long it takes to finish the training, you know, whether the verification pass or not, all of this. All these different metrics sent to the SignalFX. That is where we kind of monitor the system. Any other question which we did not address here, or any new questions?
So there was one question about the mean, max, and average thing. So we tried two different paradigms here. One was that, so each, since we have aggregation of parameters here, so the whole notion of using this sliding window was that somehow you're trying to make the system stationary around one point. When you are adding this uniform distribution of the window, you're adding some like uniform error to the model, and you make it real distribution. So you're removing the starting point there. And in this case, so like the maximum and the minimum thing that is happening is that since if you imagine that your output is coherent over time, so it should have some very good correlation with the next value. So it shouldn't really jump up and down. And that's the feature that we are using really for adding the mean and the max value here. So essentially, we changed our model to rather than predicting one single point, we are trying to predict an interval. And that's really how we are handling that.
Yeah, most of the time actually, okay, there's a new question. What was the main matrix? Oh, the kind of the matrix, is that the FP rate?
Yeah, the false positive rate.
Yeah.
So the false positive rate is that we have measured that in snapshots. So for example, initially when we started the effort, we were passing, say that we had detected 20 number of anomalies, and then we were communicating that back to the customer to make sure that this type of anomalies are real. So in fact, through practices that we had, is around 100% really accurate. Not all the anomalies are critical to be processed immediately, but for more than 99% of models, like alerts that we have, they are real and they are actionable.
Yeah. So the next question, I'm trying to understand the problem you guys will solve. I think, yeah, sorry for the, maybe we did not really give the full picture. I saw a couple of questions around that. First, this ML model, this anomaly detection model is just the one piece of really big solution, the end-to-end solution we build. Really the business problem we try to solve is to really detect, troubleshoot, and remediate end-to-end network problem. Because just as I said in the beginning, we don't want to tell the help desk it's not a Wi-Fi problem. We want to really pinpoint where the problem and what's the root cause. So actually, anomaly detection, it's not anomaly itself is not, we don't send anomalies direct to the user because it can be noisy. We actually have built another layer, troubleshooting, really to map anomalies to the root cause, to correlate with the network attributes and even potentially with the network change to find really what's the root cause causing this anomaly and take corresponding remediation actions. That's a full workflow, but anomaly detection is just the trigger of that process. Yeah, to answer your question, our goal is, the end goal is to really to remediate those problems. And we talk about this. This is called self-driving network. Our goal is to remediate the problem before user complain with the help desk. So, like I think when the network's down, it takes them maybe a couple minutes to really click around before you go to the help desk. This is really the time interval for us to take to solve this problem, potentially remediate the problem, to eliminate the customer support or operational ticket overhead there.
So anomaly detection is the beginning of trying to detect and bubble up some spatial or temporal information, like if some failures happen or something different than normal behavior has happened. But then we have the whole pipeline after that trying to narrow down the scope of the issue. And that troubleshooting is happening. And to that purpose, then it's anomaly detection is automating detection. And then it goes to the rest of the process, how to go ahead and try to understand the scope of the issue and then try to remediate the issue.
Yeah, at the end, I think half of the people probably already gone for the session. Thanks a lot for your time. It's the first time we presented here. Okay, there's one more question coming. You have a slide showing you use the Spark plus TensorFlow for model solving. Could you please elaborate on that a little bit more? Ebrahim, can you go back to that slide? Yeah, the Spark piece is yeah. So is the end user of the model calls an API endpoint that triggers a Spark job? No, we actually use the Airflow in this case to trigger, to launch Airflow is the scheduler. there are two kind of the model training. It can be triggered by the scheduler, the periodic scheduler, or it can be triggered on demand. So in that case, all of this training is launched from the Airflow. Did we answer your question? Anyway, I think thanks a lot for your time. I know maybe some other sessions are going on. We will stay a little bit longer here, and also if you are interested about any details, you can either connect with us or ping us on LinkedIn for following discussion. Thank you for spending time with us today.
Thank you, everyone, and stay safe and enjoy your day.
Yeah, stay safe there.
Thank you.
I think Ebrahim, there's no more questions. It's also over 1 hour, so we probably can leave here.
Sure, absolutely.
Okay, good job there.
Thank you. Bye-bye.
Bye.